Bismillahirrahmanirrahim. I am Hassan, and in this presentation I will be talking about the project that we did for the course Principles of Feedback Control offered at Habib University in term fall 2020. So for this project we designed two-wheel self-balancing robot, this project was basically divided into two major parts. The first part was concerned with the mathematical modeling and all the theoretical work that was involved for designing the robot itself, and the second part was the design of the mechanical structure of the robot itself. So I will in this video I will be mostly covering the theoretical part that we did for the project, and maybe in some other video I will discuss about the mechanical structure of the robot itself. So let me start off by giving you a brief introduction what the whole idea was about and what is it that we wanted to achieve from this project of ours. So the basic idea was to basically design a robot, a two-wheel self-balancing robot, as the name implies, that should be capable of balancing itself only on two wheel in case there is some sort of disturbance or some sort of error, I would say, if induced on it. So to do that we had to design some sort of controller that should be able to control the motors in such a way that any kind of disturbance should be handled accordingly. So the first step in this regard was to design a controller. In order to design a controller, the first thing we needed was the transfer function, because transfer function basically gives us the idea of how our input, which will be voltage in case of a motor, should be able to control the output that will be the angular and the horizontal displacement of the robot. So in order to derive the transfer function, our first step was to study the inverted pendulum itself, because a two-wheel self-balancing robot is a robust example of a inverted pendulum system. So let me give you a brief introduction of what exactly inverted pendulum system is, and then we will look at the equations of motions and how we derive our transfer function from those equations of motions. So this image, figure 1 that you see right here, basically gives you a fair idea of what inverted pendulum system is. Inverted pendulum system is basically divided into two parts. The first part is the cart, which is capable of moving back and forth in only covers the horizontal displacement, while the other part is the pendulum itself, which is capable of performing angular displacement, as you can see with the parameter theta, and horizontal displacement with the parameter x right here. So we had to derive the equations of motions of this system that you see right here, and in order to do so we could have used classical mechanics by calculating all the forces that were acting on this body and then derived its equation of motion. But that was quite a lengthy process, as there are a couple of many forces that are acting on this body as disturbance is induced in it. So we decided to take an alternate approach, which is of Lagrangian method. In Lagrangian method we basically only look at the kinetic energy and the potential energy that are acting on the system, and then we use the Lagrangian equation, which you see right here in equation 3, to solve for the equation of motions. So our equations of motions that we needed were obviously be in terms of the theta and x, because these are the only two freedom of motion that we had for our pendulum system. So first step we did was to basically derive the to find out the equations for the potential energy, since there is only gravitational force that is acting, that allows the pendulum system to have potential energy. So the equation 1 basically gives the total potential energy possessed by the system. And in the next step we find the total kinetic energy acting on the system by considering all the equations, by considering all the motions that were involved in the system, and then we simplified both the expression to finally get this expression, equation 1 for the potential energy, and the equation 2 for the kinetic energy. Once we had the total kinetic energy and total potential energy and the expression, the next step in this regard was to apply this Euler's Lagrangian equation. So we had to apply this Lagrangian expression 2 times because we have 2 degrees of motion, and we have to find 2 equations of motion, one for the horizontal displacement and one for the angular displacement. So by substituting the, also if you have noticed here in this expression, we have this lambda kind of symbol, which is basically which is called the Lagrange, and we have to form this Lagrange according to the parameter for which we are solving the equations of motion. For example, if we are solving it for angular displacement, then we will have to set the parameter qi in that expression as theta right here, as you can see. And similarly, if we are solving it for the horizontal displacement, then we'll have to set the parameter qi, this parameter right here, as x right here. Also, the Lagrange was simply formed by taking the difference of the kinetic energy and the potential energy, as you can see right here. So once we solved the equations and did some simplification, we were left with these 2 equations, equations of motion that you see in equation 5 and in equation 6 on the screen. So these were the 2 expressions that we get for that we got for the inverted pendulum system, and in the next step was to find the transfer function. But before we get there, we noticed that how these equations are non-linear. And since these equations are non-linear, the analysis will be rather involved and will be pretty complicated. So what we did instead, we linearized the equation. We linearized the equation according around at theta equals to 0, because this is where we want our system to be stable at, right? So these expression that you see right here basically are the linearized expression. Once substituted back in equation 5 and 6 will give us equation 7 and 8, as you can see right here. So once we had this equation, finding the transfer function was relatively straightforward task. All we did was we took inverse Laplace transform, and then we did a couple of substitutions back and forth, and the final expressions that we obtained for the transfer function can be seen in equation 12 and equation 13. Equation 12 which basically gives us the transfer function for the angular displacement with respect to the input impulse or the force, which is the u of s, and the equation 13 gives us the transfer function for the horizontal displacement x of s with respect to the input impulse force u of s. So moving on to the block diagram for the transfer function that we have obtained, we can see in figure 2, this is what exactly our complete system would look like. In this block diagram, you can see that the reference input is 0, because this is where we want our system to be at angular displacement to be 0, so that the pendulum will be stable, and also the horizontal displacement to be 0, so that the cart won't move back and forth. So this reference input is fed into the system, which is then being fed, and which in addition subtraction with the error then generates a signal error, which is then controlled to the controller. Fed into the controller, and then it is fed into the plant itself. But we can also see this symbol f right here, which basically is the impulse disturbance that I talked about earlier. U of s this u of s, the signal u of s that is fed into the plant, is generated by the addition of the controller signal added with the force disturbance that is exerted on the plant. Once that is fed into the plant readjusts itself accordingly to produce the horizontal displacement and the angular displacement, which are then fed back again using the feedback loop. And in figure 3, you can see the simplified version of the figure 2 block diagram. So yeah, I will stop this part of the video here, and we will continue with the system modeling from the next video. Right, thank you. So Allah Hafiz for now, and do take care.